Hello, I'm Jacopo Tissino from the Gran Sasso Science Institute in Italy, and I'm going to be describing to you a plan for a possible payload to send to the moon in the 2030s, roughly, aimed to measure gravitational waves. So we've heard a bit from Ettore about gravitational waves. It's a new frontier in astronomy. They have been first detected right about 10 years ago. This is what the data looked like from that first detection. You can see the characteristic shape chirping up, rising in frequency and rising in amplitude due to two black holes coalescing, orbiting each other very fast, radiating away energy until the point where they merge. So this is the kind of signal we've detected so far, but the frontiers of gravitational wave astronomy are very wide and don't encompass only this type of signal. We have many different types of sources that we might detect. Some of them are of this kind where we model the signal precisely. For example, we can do that with binary black holes because we know general relativity for the two-body problem relatively well. So we have a model. There are also some types of signals for which we don't have a model, and we can do a search for a stochastic type of signal. We can have long signals, short signals. There are searches going on with current gravitational wave detectors for all of these types of signals, and for some of them we're getting hints of detection. For some of them we are not. And yes, it's a fascinating new field. Right. So this is also why there are plans for bigger, better detectors in the future. Some of them are just making the current thing we are doing on Earth better. So this plot, I'm going to take a second to explain the axes, just so everyone is getting what is shown here. So the bottom axis is frequency, and I've put the periods for reference on top. So the current detectors on Earth are on the right of this plot. So you can see Virgo, the design sensitivity of Virgo. On the y-axis, you see the noise. Let's say a value representing the noise of the detector at any given frequency, and most detectors have a sensitivity bucket, so a region in which the noise is lower, and that's where we expect to see most of the signals. So high frequency on the order of 10 hertz, 100 hertz, 1000 hertz, that's what we can do on the Earth. But we cannot go much lower because there is a seismic field on the Earth that is just an insurmountable limit. We cannot isolate from it after a certain point. So that's why even the next generation of detector for 2030s, so let's say Einstein telescope in Europe, has this sort of vertical cutoff around 1 hertz, where we cannot just go below it. We can build something in space, such as LISA, and that gives us a bucket that's much lower in frequency, around the millihertz. And this is a detector made up of 3 satellites orbiting, following the Earth on the path around the sun. So you can notice here there is a gap between these two bands, and that's what we might hope to fill with a detector on the moon. So that's our proposal, a lunar gravitational wave antenna. So this is a sketch of what it looks like. 4 seismometers deployed in a permanently shadowed region. The red thing is a kind of sci-fi way to power them with the solar panels on the crater rim, and then power being beamed to the PSR. Somebody maybe can come up and talk to me about how unrealistic that is, or if that's realistic. I'm curious to hear about it. It's an artist sketch for sure. So these 4 seismic stations look something like this. So you have, so you're in a PSR, so the ambient temperature is already quite low, but we want to go even lower with absorption cooling systems to reach 4 Kelvin inside the sensor. Then inside, of course, so the structure is a seismometer, so it has to be anchored to the regolith, and then leveled, so you have a precisely horizontal sensor. This is a zoom in on what the sensor looks like, at least one concept for it. So the basic operating principle is that you have a inertial mass that doesn't move when the ground is shaking, and you measure the displacement of this mass from the ground in the horizontal x and y directions. The basic physical principle is a very simple thing. That's just this thing that's from the 1800s, I think. It's called the Watt's linkage. It's just a pendulum and an inverted pendulum with a rigid bar in between. And if you have this, you write the equation of motion. It has a term and another term with a minus sign, and you can tune them so that you have a resonance at a frequency that's arbitrarily low. So as long as you remain in the small oscillation limit, you have a mass that is basically inertial and not moving when the ground is shaking at any frequency in your relevant range. So what is the sensitivity of this detector? How do we estimate it? Well, when a gravitational wave impacts the moon shakes a bit in some way that is not exactly following the gravitational wave because it is an elastic medium. It has properties of a solid, so it has some inertia and some resistance, some shear modulus. All of these properties mean that it moves in a given way, given a forcing from a gravitational wave. So the response function is basically quantified by looking at taking a monochromatic gravitational wave, making it shake the moon in a simulation, ideally. We don't have very good simulations of that yet, but that's the principle. And then see how much is the horizontal displacement that's caused by this gravitational wave. So the gravitational wave is measured by that quantity there, the strain. So that's kind of delta L over L in terms of units. So it's dimensionless, typically on the order of 10 to the negative 21. So very small relative displacement. And then you're looking at a baseline length that is just the horizontal motion in meters divided by this dimensionless. So it's always a length, and it's frequency dependent. At some frequencies, you may have resonances and things like that. For example, in the millihertz band, you have the normal modes of the moon, of the whole moon. And then basically the noise on the strain, going back to what we actually want to measure, the gravitational wave strain, is going to be given by the noise we have on the measurement of the displacement. That's a sensor property, divided by the baseline length we're working with. So the displacement noise, roughly speaking, these are two noise models for two different concepts of the detector. As you can see, it's all very preliminary. These are all power laws and very clean things. So one concept is an interferometric readout. The other concept is the one that was shown in the sketch before, so with this superconducting quantum interference device. Anyway, you can see that both of them have this sort of shape where you have a power law going up. That's due to thermal noise of the suspensions, that you always have that. So your sensitivity gets worse when you go to lower frequency. And then it sort of tapers off at higher frequency. And then you're dominated, instead of by thermal noise, by, for example, if you have the interferometer, at some point you reach the shot noise limit, where it's about counting photons, and that's based on the power you get with the interferometer. With the squid, it's a bit different, but still same sort of shape, right? The thermal noise is why we want to go in a PSR, because that allows us to get things very chilly. As we've heard several times this week, PSRs are very cold and relatively stable, not perfectly stable, depends. Maybe I didn't know about the double PSRs, but that seems very useful for this purpose. Right, so knowing the actual response function is tricky. We need better simulations. For the moment, we are working with some simplifying assumptions, but in principle, we need to know the details of the local topography. Why is that? I hope, right, yes. Because our band of interest is not where the normal modes of the moon lie. So those are all those peaks you see on the left there, but it's lower to the right. So this sensitivity here doesn't look very impressive. That's because that's not our final design sensitivity, but that's the sensitivity of the mission called Soundcheck. There is a pathfinder we hope to send to the moon through ESA. It's one of the missions in the reserve pool of activities. So as we've heard, it may fly, it may not. We hope it will. Thank you. And you can see it's not probably good enough to actually detect gravitational waves, but it's much more sensitive than anything that's been on the moon yet. So it can give us some insights in the topography and seismic fields in a PSR. After that, the full design sensitivity with instruments that have not been developed yet, that are in the stages of testing and construction, that's the sensitivity we may reach. And you can see that the bucket of interest is actually not where the normal modes of the whole moon lie, but it's a couple orders of magnitude higher in frequency. At those frequencies, the response of the moon is not based on the full radius of the moon, but it's if you compute the baseline length I was showing before, it's on the order of 110 kilometers. So you're looking at a much smaller region of the moon that's oscillating. But that's a region of interest, both because at lower frequency, we have other instruments that do it better. And yeah, because seismometers are intrinsically more sensitive in that band. Right. Science we might do with it, just a quick glimpse. These shapes here that are drawn on top of the sensitivity noise curves are the signals from binaries of various masses. The further right, the lower in mass. So these spectra are the ones on the right are ones that have been actually detected with gravitational wave detectors. The ones to the left we have not detected. Those are intermediate and supermassive black holes. They could be very interesting as a source of gravitational waves and to learn whether they actually exist, intermediate mass black holes. We don't really know. So that's about all the time I have, I think. And this is a link to the white paper where all of the science that can be done with LGWA is outlined. So if you're interested, check it out. And thank you.
We have room for a couple of questions. So.
Thank you. Cesare Gravasat, What's Research Institute, interesting concept. So we know that from Apollo measurements, there are moonquakes on the moon, and most of the seismometers were on the equatorial region, of course. We don't have yet seismometers on the northern and southern poles. If we will measure moonquakes, would that be a major problem?
Right. Yeah, no, of course. This is something I didn't have time to get into, but it's a very important issue for us. So for one, this sort of instrument will give us good measurement of moonquakes. So it's good for lunar seismology as well. On the other side, yes, moonquakes would be a problem. That's kind of the reason we have 4 seismometers planned instead of 1 to sort of do an active noise subtraction, because the moonquakes are a source of noise for us in a sense. So having more stations allows us to potentially, I mean, that's of course remains to be tested and developed in much better detail, but the idea is that we subtract them as if they were a source of noise. Right. Thank you.
Hi, Carl Hibbs, APL. I have an engineering question for you. Do you have an estimate on the size, weight, and power for each of the stations that you propose, each of the 4 stations?
Oh, that's a great question. So I see the paper that's linked in there that's looking into the payload has much more detail on that. I believe that these are relatively low power things. So we're like order of magnitude is like 1 watt, 10 watt. So low power stuff. But do check out the paper for the details and the actual precise estimates, because I haven't actually worked on the design of the detector. So yeah, cannot be 100% confident. There's a question there. We have time.
Hello, thank you for your talk. I was wondering if you were expecting any interference because of the regolith inside the PSR, the loose regolith, or if you're expecting any magnetic interference, and if so, how are you dealing with that?
Right. So the loose regolith, might be a problem. I honestly am not sure. We're looking at low enough frequency, maybe that the regolith does not pose too big of a problem for us, but that remains to be studied in detail. About the magnetic interference, I also don't really have an answer for your questions. I would hope that the shielding can be made around the detector such that you are not really concerned about that, but for sure that's something to be looked into. Thank you.